record. Okay. So you said one of the points is 1, 2.
Yeah.
We're dealing with exponential growth or decay?
Growth. And the other point it gives is 0, negative.
That's the key point.
Yeah.
Why is that the key point? Because x is equal to 0. And my equation is going to be y equals ab to the x plus or minus k, or just ab to the x?
I don't know. I think AB to the x.
Yeah. And the only difference is if it's decay, it's like that.
If what?
If it's decay, it's like this. In other words, it's as if this were reflected about the y-axis.
Okay. I have a question about this. Does the asymptote matter?
Yes, it definitely does. If the asymptote is the line y equals 0, there's no vertical shift. If the asymptote is the line y equal minus 2, then it would be that.
Okay. Well, this problem has an asymptote of y equals negative 4.
Okay. So it's abx minus 4 to start with. Okay. Now, normally, if I set up an equation based on that point, it would be 2 equal ab to the 1 minus 4, correct?
Mm-hmm.
And the other equation would be minus 2 equals ab to the 0 minus 4. Well, normally when we have two equations and two unknowns, we can solve by treating them as simultaneous equations. But in this particular case, this equation right here always gives us the solution for A. The reason being is that whenever you take any variable to the 0th power, it's 1. So I can figure out what A is based on that equation alone. One equation, even though there's two variables, one variable really doesn't act like a variable. Because B to anything to the 0th power is 1. So in this case, A is equal to 2, based on this equation alone. Okay? You get that? So if A is equal to 2, now I can solve this equation, because I know that 2 is equal to 2b to the 1 power minus 4. So b has to be equal to 3 after you do the algebra. So now my specific equation for this is y equals 2 times 3 to the x minus 4. So that satisfies both points and the horizontal asymptote that's at y equal minus 4. Now, all of these, the way to do it is to always work with that point first, because that point has an x value of 0, so b to the 0 is always going to be 1. So I can solve for one of the variables as long as I start there. If I start right here, I can't solve for a variable because b to the 1 is b, whereas b to the 0 is always 1.
Okay. We just try another.
Yeah, I think I've seen all these before. I had a student the other day that showed me all of these vertically shifted exponential curves. So if you can tell me where the horizontal asymptote is and what 2 points are on there, we can come up with the equation.
Excellent. Okay, so the horizontal asymptote is at 1, so y equals 1. And then the 2 points are 0, comma 3, and negative 1, comma 7.
All right. So the general equation taking the asymptote into account is what?
Y equals ABX plus 1.
Uh-huh. Now what?
Now we substitute in 0, comma 3.
Okay.
Or the 3 equals A, B to the 0 plus 1. And then after the algebra, you get 2 is equal to A.
Okay.
Right?
Uh-huh.
Then you substitute that in plus the 2 with 7, or negative 1, comma 7. 7 is equal to 2b to the negative first plus 1. And then solve that. How
do you solve that right there?
Oh, b 1/3 because
Uh-huh.
you multiply
Yes.
negative 1, right? And then you
Well, there's a couple of ways to do that. We could say 3 equals 1 over b, which means b equals 1/3. Or the way the student did the other day, which I hadn't really seen before, but I kind of like, is taking both sides to a power that forces the b to be isolated. In other words, if I take both sides to the -1, well, -1 times -1 is just b, and 3 to the -1 is that. So the only thing you have to be careful about is how would I solve the following, because this comes up. If I'm going to use that technique, what would I do here?
would you multiply by the negative 2?
I would exponentiate both sides, not by -2, but by -1/2.
Oh, okay.
And the reason is that that -1/2 times the -2 is 1. So I get b equals 1 over the square root of 3 if I were solving the other problem.
Okay.
Okay?
The other problem, could you also solve that by multiplying by -1 and then taking the square root? Or would that just be like way more complicated?
So if 3 were equal to b to the -2, so if I exponentiate both sides to the -1, I now get b squared equals 1/3 square root of both sides. Yes, same thing. b equals 1 over square root of 3. Okay.
So the next problems I have deal with compounded interest.
Okay.
So the first one says that you invest $1,500. The local bank gives you the option of following 4 plans.
Okay.
How much money will you have after 5 years of each plan? And the first one has 3% interest, which is compounded annually. second has 2.8% interest, which is compounded quarterly. The third has 3.7% interest, compounded daily. And the last one gives 2.5% interest, compounded continuously.
There's your answer right there.
I know.
But let's do the math.
Kind of a funny problem looking at it.
Huh? Well, they didn't put the numbers very close. In other words, they could have at least put the numbers a little closer so that we had to do the math in order to answer the problem. These numbers are so far apart that we do not have to do the math in order to look at the problem. Of course, I might be surprised, but I don't think so. We've got three equations. We've got compounded annually, where the amount is equal to, do you know these three equations?
Well, it would be the actual equation, or
Well, there's actually three equations. There's one for compounded annually. There's one for compounded more than annually.
Oh, we just got a basic equation. I don't know how we can.
Well, that actually works also.
Yeah.
In other words, there's your compounded more than annually. Compounded annually is just 1 plus r to the t. Compounded continuously, ERT. So there's your three equations. So let's do the first one. 3% compounded annually. So our amount is going to be 1,500 times what?
Times 1.03 to the t power. So that's 5 years.
Yeah, do you have your calculator?
I do.
Let's come up with a number on that.
So $1,738.91.
Okay.
For the second one, it would be $1,500. 1 over n, since would that be 2.8 over 4?
Yes. Yes, exactly.
So then that's 1 plus 0.7?
0.07.
0.07? Okay.
Hold on. No, let me think about that for a moment. It's, let's see, if I divide this by 4, it's 0.07. And what's the TN become?
The TN would be 20, because it's 5 times 4.
So let's have a number on that.
Okay.
You see why it's 1.007? Because the interest rate is 2.8%, which is 0.02, excuse me, it's 0.28. If I divide that by 4, the number of times I'm compounding it, I get 0.007.
Oh, I get it, yeah. I did it wrong. Alright, so the answer for that one is $1,724 and then 57 cents.
Okay. Let's do the third case. Compounded daily. What's this part here? In other words, what goes inside the parentheses?
1 plus, would it be, Why 3 point? Oh, 3.7 is the rate.
which is the same as 0.037,
Yeah.
divided by what?
Would it be 365?
Yeah. To what power?
Oh gosh. 365 times 5.
Uh-huh. Yeah, these seem almost a little ridiculous when you end up taking a number to the 1500 or the 1800 power. But that's what you got to do.
Alright, well.
It's actually it's a little more than 1800 power.
Yeah, 1825.
Okay.
According to my calculator.
Yes. Sounds right.
So that gives you 1,800 and that seems like a little smaller than I think. $1,803.59.
It's lower than you expected it to be?
Yeah.
Me too, actually. I thought it was going to be bigger than that also. I'm surprised that compounded quarterly there is that close to a much bigger number compounded more frequently.
I wonder if I did the math wrong. So, the number I got for the, what's it called, the rate, was 1.000101.
And you took that whole thing to the 1825th power?
Yeah.
Multiplied it by 1500.
Yeah.
Sounds right.
Alright. So then for the next one would be 1500 oh goodness. Okay, so 1 and then oh no, this is E. This is the RT. So E and then the rate would be 0.25, right?
Thinking for a minute what it should be here. This is the correct equation, right?
Yeah.
Okay. E to the RT, so it's got to be E to the 1.025 times 5. It doesn't seem right to me for some reason. Couldn't. In other words, it's not going to be 0.025 times 5. That certainly isn't going to give you. What number does this give you? That's not going to be right either. I'm going to have to look in my book for a moment. I haven't done a continuous compound in a while, and this doesn't appear to be right. This number should, continuous compounding is not that much better than daily compounding.
A lot better.
Huh?
It's almost a lot better.
Well, it shouldn't be. That's what I'm saying is that it shouldn't be that different. But I've got to find in my book where this equation is.
That's the one we use in class, though. I mean, I have them all written down and they're all straight.
Yeah. Okay, I've got. Question is, what is the R? Now let's try 0.025 as the R. What do we get? In other words, instead of making it 1.025, it's really just R. That's where I'm going wrong. In other words, this R here is the same as that R, and it's the same as that R. So I'm pretty sure that it's going to be,
Yeah, that's what's a lot.
there you go. What does that number give you?
That gives us $1,699.72.
Yeah, that makes more sense. And notice that that's the least. Well, it's not that surprising because it was 2.5, which is the least rate, and the highest rate was 3.7, and that gave you the best result. So it kind of shows you that all of the differences in that aren't that great. In other words, what gave us the biggest number was the highest rate, not the fact that we were compounding daily. It would have been a little more instructive of a program or of a problem had they put these numbers a little closer together. Then we could have really seen what the difference was between annual, quarterly, daily, and continuous. The fact that they gave us such different rates, we didn't really see the difference at all.
What does continuous compounding mean exactly? What does that mean?
It means exactly that it grows as a function of how much is there at all times. In the same way that bacteria grows that way. And in the same way that populations grow that way. All of them grow continuously, where for a while at least. So when money is growing continuously, it is always earning interest based on exactly how much there is there. So if you invest $1,000 at 12% a year, let's say, well, at the end of the first month, you've got 1% more. So you've got 1,010 at the end of 1 month. So at the end of 1 month, you're earning on that amount. Well, that would be compounded monthly. Compounded continuously means that 2 seconds after you invest it, it's worth a little bit more than it was, and it's now earning interest on the amount that it's now worth.
Okay.
In other words, it's like somebody was, the real example would be if you did daily compounding compared to continuous compounding. And people might like to make you think that the continuous compounding is greatly different, but it's not. Continuous compounding barely outperforms daily compounding.
Why is that? Because, I mean, you're using the...
Well, because daily compounding compounds 365 times per year. Continuous compounding compounds an infinite number of times per year, literally, but it doesn't give you that much more improvement when you go from daily. I mean, the really good problem that they should have given you was these 4 examples all with the same rate. In other words, if we did them all at 3%, how would it compare? And that would have informed you a little bit more as to the differences between annual, quarterly, daily, and continuous. The way they did it, where they switched in 4 different rates, didn't tell you anything.
Yeah.
Now, if they did it all at the same rate, 3%, this would have won, but just barely. It would have barely won over this, which would have beaten this, and would have beaten that. So it would have gone 4, 3, 2, 1 if we were at the same rate for all 4 different methods.
What is E is equal to 2 point something, right?
Here's the definition for E. That is what E equals.
That's exotic.
It is exotic because you've never had limits before. And it's an irrational number. It goes on forever like pi does. But you can see what happens. As x goes to infinity, this what's inside the parentheses gets closer and closer to 1. But then you're taking it to a number that gets closer and closer to infinity. So it's not real clear what would happen. I mean, you have to admit that that's an interesting problem. In other words, if I took 1 to infinity is equal to 1. But 1.0001 to infinity is equal to infinity. So what happens when this gets closer and closer to 1 as this gets bigger and bigger and bigger? Well, you end up getting 2.71. It hones in on that particular number, which is kind of interesting. What is so special about that number? Well, there's only 2 numbers in all of math that we know of that are special, and that's pi and E. And they may equally be important. But pi is simple to define. It's the ratio of the circumference divided by the diameter, whereas E is not so easy to define. That's the definition of E.
That's really cool, though.
Yeah, it is. I used to tell people that this reminded me of when I read Superman comic books when I was a kid, because you have basically an irresistible force meeting an immovable object. This thing's trying to go to 1 as x gets large. And like I said, 1 to infinity would be 1. But 1 and any additional amount to infinity is going to go to infinity. So what happens to this peculiar beast? Well, it goes to exactly 2.711 or whatever the numbers after 71 are. In other words, it doesn't go to 1 and it doesn't go to infinity. It goes to this very special number. And it's because this process right here, this exponential process that you'll notice is very similar to what we've been doing. We've been taking 1 plus a rate divided by n, and we've been taking it to nt, and this tends to get very big. This tends to get very small. And that's the same process that E is calculated by. That's why continuous growth has E in it. Because basically n goes to infinity, and then you have that.
Oh, so cool. That is cool. Art is cool. Alright.
Oh, it's 4. I forgot.
No, I didn't even notice.
We're only doing half-hour sessions. Yeah.
Yeah. Alright.
All right. Sounds good. I will talk to you on next Monday.
Alright, excellent.
All right, Sarah. Have a good week. Bye-bye.